Section 9.3 is the integral test and p-series. In this section, we're going to learn about a new test that we can use to determine if an infinite series diverges or converges. And then we're going to learn about p-series and how to determine if a p-series diverges or converges by just looking at what p is. Let's start with the integral test. Now the integral test says, let's let a sub n be an infinite sequence of positive terms. If a sub n is equal to a function where that function is continuous, positive, and decreasing for all x greater than or equal to 1, then we can rewrite the infinite series as an improper integral. So the integral test says if you can show that you are continuous, that you are positive, and that you are decreasing for all x's greater than or equal to 1, then you can rewrite your infinite series as an improper integral. Once we have it written as an improper integral, we evaluate this improper integral, as we did in section 8.8, and if the integral converges, the series also converges. If the integral diverges, the series will also diverge. Let's look at problems where we're using the integral test to determine if a series converges or diverges. The directions state to confirm that the integral test can be applied, then use the integral test to determine the convergence or divergence of the series. So when it says that we need to confirm that the integral test can be applied, what we need to do is show that it is continuous, positive, and decreasing for those x's greater than or equal to 1. So let's go ahead and do that for number 1. The first thing we want to do is take a sub n and rewrite it as a function. As a function, f of x, we would say 1 over, instead of n, x squared plus 1. Now I have to show that it's continuous, positive, and decreasing. For continuous, I find the domain. Well, how do I find the domain? Since this is a rational function, I have to set the denominator equal to 0, solve for x, and any real number I obtain, I must exclude from the domain. So my denominator is x squared plus 1. If we set it equal to 0 and we try to solve for x, subtract 1, take the square root, and you end up with plus or minus I, because the square root of negative 1 is imaginary. Well, since that is imaginary, then there's no numbers to exclude from my domain, which means that the domain of this function is equal to all real numbers. Since my domain is all real numbers, therefore I'm going to be continuous for x's greater than or equal to 1. The next thing I need to do is show that I'm positive. Well, that's actually really easy. All you have to do is look at your function. Well, look at this numerator. The numerator is always a positive number. The denominator, well, it's something squared plus 1, is also always a positive number. Well, a positive number divided by a positive number is going to equal a positive number. Therefore, you know that you are going to be positive for x's greater than or equal to 1. The last thing that you need to show is that you're decreasing. Well, how do I show that I'm decreasing? An easy way to show that is to find the derivative of the function. So I'm going to rewrite f of x with a negative exponent. If I write this as f of x is equal to x squared plus 1 to the negative first, bringing it out of the denominator and moving it up, if I were to take the derivative, I would get f prime of x is equal to, using the chain rule, negative 1, and then x squared plus 1 raised to the negative second, times the derivative of the inside, which is 2x. Let's rewrite it without the negative exponent. We get f prime of x is equal to negative 2x over x squared plus 1 squared. Now the denominator is always positive. Why is it always positive? We're squaring it, and so we know we're going to get a positive number all the time. What about the numerator? Well, the numerator is going to be negative for x's greater than or equal to 1. Why? X is greater than or equal to 1 because our counter starts at 1, so I'm only looking for those x's that are greater than or equal to 1. Well, a negative divided by a positive is going to equal a negative number, which means that I am going to be decreasing for x's greater than or equal to 1. Why decreasing if we're negative? Again, remember, the derivative is slope, and so if we have slope of the tangent lines that are negative, then our function is decreasing. Now that we've confirmed that the integral test can be applied, let's actually use the integral test to determine whether this series converges or diverges. Well, how do we do that? First, write the series and then write my improper integral. My improper integral is going to be the integral from 1 to infinity of, and instead of writing it in n's, we now write it in x, 1 over x squared plus 1 dx. Then what we need to do is rewrite it as a limit statement and integrate. Well, we're going to do both at the same time. Is this something that we can integrate? Yes, its basic form, it's the inverse tangent. So we know that here, u squared is equal to x squared, u would equal x, and du is equal to dx. Perfect, that's exactly what I have. A squared is equal to 1, and a is equal to 1. Therefore, we say that this is equal to the limit as c goes to infinity, because remember, you want to pick that variable to replace infinity. And then if I'm integrating this, we know that this is, again, inverse tangent, so it's going to be 1 over a. Well, 1 over 1 is just 1, I don't need to write that. And then it's just inverse tangent of u over a. Well, x over 1 is just x. And then this gets evaluated from 1 to c. So again, we replaced infinity with c, and then placed c as that limit of integration. Now, what is the limit as c goes to infinity of the inverse tangent of c minus the inverse tangent of 1? Well, what is the limit as c goes to infinity of the inverse tangent of c? Well, recall, the inverse tangent looked like that cube root function. It looks like this, and it has that horizontal asymptote here at y equal pi over 2, and one down here at y equal negative pi over 2. Therefore, as we're approaching infinity, my y values want to be pi over 2. So this is equal to pi over 2 minus, well, the limit as c goes to infinity of the inverse tangent of 1 would just be the inverse tangent of 1 because it's a constant. But what is the inverse tangent of 1? At what angle do I get 1 for tangent? Well, that's at pi over 4. Now we finish it off. Pi over 2 minus pi over 4 is equal to pi over 4. So my improper integral gave me pi over 4. And what did that mean? Well, since the limit existed here, that means that the integral converges. And since we're using the integral test to determine if the series converges or diverges, and what we were told is that if the integral converges, the series also converges, we can now say, therefore, our series converges by the integral test. First, we had to confirm that the integral test could be applied by showing that this is continuous, positive, and decreasing for x's greater than or equal to 1. Then, we made our infinite series into an improper integral, evaluated the improper integral, and determined that that improper integral converged. Since the integral converged, the series does the same thing. The series converged by the integral test. Now please note that even though the limit of the integral converges to a number, so here the limit of the integral gave us pi over 4, the series typically does not converge to the same number. So the sum of the series may or may not be that pi over 4 in this case. So usually they're not the same number. So please understand that that's not the sum of the series. They're two separate things. And you won't be asked to find the sum of these series if the integral does converge by the integral test.